A binomial is the difference of two perfect squares if it meets both of these conditions. First, both terms must be perfect squares. And second, the signs of the two terms are different. So one sign is positive, one sign is negative. And if you use the intro video, you can provide some examples of a difference of two perfect squares. There were lots of examples of squares there. How about z squared minus 36? How about 64 minus t to the fourth? These are just some examples of a difference of two perfect squares. So how do you factor the difference of two perfect squares? If you took the notes for section 5.4 with the special products, then that would make this a little bit easier, but if not, it's not a big deal. Because a squared minus b squared is going to be two binomial factors. And they're going to be the sum and difference of what's being squared. So for the first term, that's a squared. So the first term of both binomial factors will be a, because a times a is a squared. And the second term is going to be b, because b times b is b squared. And if you're not sure why that works out, you can multiply those together to see what happens. So when you multiply a times a, that's a squared. A times minus b is minus ab. Then if we multiply b times a, that's positive ab. And b times negative b is negative b squared. So you see why the outer and inner factors are going to cancel each other out as terms here, leaving just a squared minus b squared. So that's why we have those two binomial factors for the difference of two perfect squares. So let's use those factors to factor differences of two perfect squares. So the first step is going to be to rewrite so that we can recognize what's being squared, okay? Or if this is actually a difference of two perfect squares. So let's see. Can x squared be written as a square? Yes. 9 can be 3 squared. So yes, this is a difference of two perfect squares, and now we can factor that. So we'll have two binomial factors, a sum and a difference of the first term that's being squared and the second term that's being squared. Okay, our next example, can we rewrite this as a difference of two perfect squares? So y squared is y, and 16 is the square of 4, and 25 is the square of 5. So yes, this is the difference of two perfect squares. So we will have the sum and difference factors of y and 4/5. Then our next example, can we write this as a difference of two perfect squares? 4 is 2 squared, and x squared is x squared. And 1 is 1 squared. So yes, that means we will have two binomial factors, sum and difference of 2x and 1. Then our next example, can we write this as a difference of two perfect squares? Let's see. 36 is 6 squared, and a squared is a. 49 is 7 squared, and b squared is b squared. So yes, this can be written as a difference of two perfect squares. So we can factor it as the sum and difference of the first term, 6a, and the second term, 7b. All right. Then our next example, can we write this as a difference of two perfect squares? X squared is x squared, and 5, nope, that doesn't work. So if this is not a difference of two perfect squares, then this is not factorable. Only if these were perfect squares could we factor. All right, then our next example, we want to see if we have a difference of two perfect squares. But there's a problem here because there's the first term is negative, so that means we have a special GCF. We have to factor out a negative, and these two terms actually have 4 in common, so we have to factor that out first. So let's factor out that GCF. Divide that from each of those terms to see what remains. So for the first term, that's y squared. For the second term, the negative is going to divide to a positive 1. So now we want to see if we can factor the y squared plus 1. So can it be written as a difference of 2 perfect squares? Oh, they have the same sign. So that means we can't factor that. Does that mean that this should be a prime polynomial then? Well, no, because we did, in fact, factor out a common factor of -4. So this polynomial does have factors other than 1 times itself. I just cannot further factor the binomial that remains. All right, some more examples here. We want to see if we can factor these. Okay. First thing I noticed, though, is, again, we have a common factor, so we have to factor that out first. Both terms have an x. So let's factor out the GCF of x, divide that to see what remains of this binomial. So for the first term, that's going to be 4x squared when you use the quotient rule there. And the second term, that's going to be 49. The x's cancel out multiplicatively. Okay, so now we want to see if we can factor the 4x squared minus 49. Can we rewrite that as a difference of 2 perfect squares? Well, 4 is 2, and x squared is x, and 49 is 7 squared. So yes, we can. Don't forget the GCF. And then we'll have 2 binomial factors, the sum and the difference of the first term, 2x, and the second term, 7. Then our next example, there's no GCF. Although, if we wanted to, we could rearrange the terms and then factor them that way. But it looks like we can just rewrite this as 7 squared minus x squared so that we can factor the difference of 2 perfect squares as the sum and difference of the first term and the second term. So if you want to rearrange the terms, factor out a negative, and then factor the binomial, that's fine, but this is also fine too. So if you factor out the negative, then this will look like negative x minus 7 and x plus 7. Factor order doesn't matter. Okay. Then our last example here. Is there a common factor for these terms first? Okay, there is. So we'll need to factor that out first. Both of these share a factor of 3. So we're going to factor out a GCF of 3. And when we divide, that goes in 16 times x to the 4th, and the second term that divides to 1. So now I want to see if I can factor this remaining binomial. Can I write this as a perfect square? Well, 16 is 4 squared, and x to the 4th could be x squared squared, right? And 1 is a perfect whatever I want it to be because it's a multiplicative identity. All right, so we've got our GCF, and now we know that we'll have 2 binomial factors for the difference of these 2 perfect squares. That will be the sum and difference of the first term, 4x squared, and the second term, 1. However, this is not fully factored, is it? Because this binomial factor actually is another difference of 2 perfect squares, right? If we were to rewrite that, we could write it as a difference of 2 perfect squares, 2x squared and 1 squared for this. So that means we can factor that even further. The first 2 factors are not going to change, but that third factor will be 2 factors, the sum and difference of what's being squared. The first term is 2x, and the second term is 1. And that finally completes the factorization of this polynomial.